Okay, so let's go ahead and read a few directions. So unconstrained optimization of one variable, find the x values of x that maximize the following function. You can assume that extremum you find is a maximum and don't need to check the second order condition, but if you know how to check it, do so. Yeah, so you maximize, minimize, but we don't care about the minimum. We only care about a maximum over here. And we do have some rather strict procedure from Calculus 1. They're telling us that we can ignore that. This is basically, for the most part, straight up, take the derivative and set it equal to 0. Unconstrained optimization. That just means the domain for all of them are all real numbers. Constrained optimization. Am I getting that right? Optimization with interval constraints. I know that I wrote everywhere, but interval constraints or constrained observations just means that we have one or more domains. A constraint is like a line or another graph or something. Oh, we get to that next, but you kind of have two. One domain is all real numbers. The other one is like the bottom of a fraction, which we don't really have in this class, or a square root, where x cannot equal 0, but unconstrained optimization really just means follow the domain of the function. Unconstrained optimization just means that we don't assign another domain. It's just whatever natural domain is for the function. And once again, the domain for all of those are parabolas. Hopefully it's obvious. A quadratic function and a parabola are the same thing. Yeah, a parabola, the domain is all real numbers, negative infinity to infinity, both holding water, dumping water. Yeah. So unconstrained optimization, what does that mean? It means we're maximizing. It means that you take the derivative, set it equal to 0. A, the derivative is negative 2, x minus 2 to the 1 times the derivative of the inside. Yep. So that is the derivative there, yeah. We can, it doesn't matter. We, at this point, not that it simplifies, it's easy, but we don't really care about much simplifying. How do we maximize? Remember, we don't care about any second order condition, and we don't even have to review much what that is. When you maximize or minimize, you just take the derivative, set it equal to 0. We should review, so I should straight up say it. You always take the derivative, set it equal to 0, solve for x. I'm not going to write all this out, but take the derivative, set it equal to 0, and solve for x. You know, it's kind of the key to all related rates, optimization, all of that from Calc 1. This is the optimization portion here, yep. So sometimes I just stop and make a point, but if we write it again for a, the derivative is negative 2. Yeah, x minus 2, take the derivative, set it equal to 0, and solve for x. Distribute the negative 2, but who cares? You just divide both sides by that. Yeah, and we're just to assume, we can see by looking at it that all of them are negative parabolas. All of them are parabolas that dump water. Negative, negative, negative. All of them are parabolas that dump water. So where the slope equals 0, I hope we know that the derivative is the slope as a rate of change. The derivative is the slope, set it equal to 0. We find the x value. We could plug it back into the original function to find the y value, yeah. But we do have x equals 2 is going to be a maximum. And yes, why don't we go ahead and do that? So the same problem, f of x equals negative x minus 2 squared. If we have a maximum at x equals 2, we plug that in. Yep. And the maximum is at 0 there anyways. But the maximum is the 0.2 comma 0. That is the, we have a max. Yeah, we don't care about absolute max or local max or anything like that. Yes, we have a maximum of 0 and it's located at x equals 2. Okay, so we can fly through all these really quick. They're all the exact same exercises, all they are. Yeah, so b, the derivative is Negative 2x plus 6. Take the derivative, set it equal to 0. We're not thinking. We solve for x. We don't have to show any work. Who would show work? X equals 3. Yep. If you plug it back into the original function, you get the maximum at x equals 3. So just plug it back in. And moving right along, what is maximize? It is take the derivative, set it equal to 0. Who cares? Do a product rule. They make a point here. It doesn't matter if you do the product rule or if you multiply it out and then just do the general power rule. The product rule is easy. I don't know why I care, but just we just go ahead and FOIL that. I see negative 2, negative 3. I see negative 5x plus 6. Put the negative on through that. Okay, so take the derivative finally. We did just multiply both sides by d over dx, even if we don't write it. Take the derivative, set it equal to 0, solve for x. I feel like it's so obvious that I'm just trying to get past this video here. Yes, but we get x equals 5 halves is the answer. And if we plug that back in to the original function, we get the x value. We know what a graph is, yeah. Yeah. The x value is where the maximum is located. The x value is not the maximum. The maximum is a y. So the x value is where the maximum is located. Plug it back in, and the y value is that maximum. Maybe just to do it, we just go ahead and plug that in there. So 2.55 halves, just taking a little bit of time with this thing here. What is the original? We're still doing C. This right here is the original. Yep. Okay, so plug 5 halves in there, plug in 5 halves, plug in 2.5. Yeah, so we start doing like a fraction review, which is just so silly. I see 4, I see 5 minus 4 over 2. I see 5 minus 6 over 2 equals negative a half. Negative a half equals a fourth. We have a max. Write this somewhere. Yep. We have maximum is going to be a fourth. Maximum is going to be a fourth at x equals 5 halves. So that's like one full problem there. Okay, so what do we have for 4 and 5? Yeah, so 5 will finally be partial derivatives. Optimization with interval constraints. Find the value of x that maximizes the following function there. Let me just see if I can fly through 4. So optimization with interval constraints, it just means that it has to be 0. Okay, so we do remember this basic rule. I guess we'll go ahead and we'll just start the next video with this right here. So once we kind of do this guy, then we're going to finally talk about partial derivatives for a little bit.